In this video, we're going to use a simulation-based strategy to compare several groups. So notice the fact that we have several groups here means that a regular t-test, like a two-sample t-test that we've been doing earlier, won't work. So it's right there in the name. A two-sample t-test only works when you have two samples. But we can also look at the test statistic to see why that's true. The numerator of the t-statistics is just a difference in the means, the mean for group 1 minus the mean for group 2, but that's only a good summary when you only have two groups, right? You can't subtract three different groups, for example. So we're going to have to use a different strategy here. So this example was seeing whether simple questions about a person's diet could predict their omega-3 blood levels. So they looked at 30 generally healthy adults from the US who weren't taking any kind of omega-3 supplements. They ended up with only 27 participants who completed the study. That's pretty common to have people drop out along the way. And they categorized them into 5 groups based on their self-reported consumption of tuna or other non-fried fish. Then the response variable was their omega-3 fatty acid levels, and those were measured as a percentage of all the red blood cell fatty acids that are good fats via a blood test. So I'm not sure exactly what that means, but it's a quantitative variable that's looking at a percentage. So you can see these groups are ordered from A to E. So A is the group that eats the least amount of fish, less than once a month, and E is the one that eats the most amount of fish, so more than twice a week. And we can already kind of see at a glance that some of the variability is being explained here. So first we can see that the group means are not all the same. So it does seem to make a difference, right? Different levels of fish consumption lead to different levels of fatty acids. We can also see that the amount of variability within the groups tends to be smaller than the amount of variability overall. So that would indicate that our predictions are more accurate if we know somebody's fish consumption than if we were just guessing based on the overall mean. So we do have some amount of variability explained, but how do we decide if this is statistically significant? In other words, is it plausible that these differences in the means just occurred by chance in this particular sample? So our null hypothesis here is that there's actually no association. There's no relationship between these two things. So it would be no association between the omega-3 levels, which is our response. No association between the omega-3 levels and fish consumption. So this is the self-reported fish consumption, which we're using as our explanatory. If we wanted to write this in symbols, we would write it in terms of mu, because again, we're comparing means, but instead of just having mu1 and mu2 like we had for a two-sample t-test, here our null hypothesis will be that all of our means are equal. So it doesn't matter which group you're in, A through E, because all of the means are the same. The alternative hypothesis is that there is an association between these two. So in other words, knowing somebody's fish consumption would help you to predict their omega-3 levels. And if we wanted to write this with symbols, we would just say that at least one of these is different. At least one mu is different. So notice an association doesn't necessarily mean that all of the groups are different from each other, just that at least one is different from the rest. So we're going to do the 3S strategy for this simulation. So we're going to start off by calculating a statistic. That's just one number to summarize the sample. So we can't do a difference in means, which is what we would do for a two-sample t-test, because again, with more than two groups, if you've got 5 different fish consumption levels, then a difference isn't going to cut it. So we've only learned one statistic so far that allows us to summarize the strength of an association even when we have multiple groups, and that's the R-squared statistic. So we saw earlier R-squared works even when we have multiple groups. And we've seen how we can calculate this using JUMP, but I'm just going to do it with an applet real quick. So we're going to use an applet from Rossman and Chance. And we're going to do a randomization test for a quantitative response, the one that says multiple groups. And I'm going to copy and paste the data, and the data are given a couple different ways. I'm going to use this column where the omega-3 levels are given as percents, and fish is just given as a category A through E. I'm going to copy that. I'll clear out the data that's in here and paste it. Notice that I have my response variable coming first, so I'm going to click this little button here to tell it that I'm giving it response and then explanatory, and then I'll click use the data, and I can see my data is coming up here. And it's annoying that it's not putting the categories A through E in order. It doesn't really matter, but it is kind of annoying. And the statistic that I want to calculate is my R squared. So I'm going to come down here to statistic and pick R squared, and it is 0.506. So with an R squared value of 0.506, that means that just over half, 50.6% of the variation in omega-3 levels can be explained based on someone's self-reported fish consumption. So that value, R squared equals 0.506, is that something that could occur just by random chance, or is this convincing evidence of an association? The simulation that we're going to be using is pretty similar to what we would do if we were comparing two groups. So we're going to start off by writing the response variable on cards. So we've got 27 data values. We're going to write 27 omega-3 levels on our cards. And then we'll shuffle them all together. Notice that I'm not labeling them. I'm not labeling them A through E because as I'm shuffling all these groups together, I'm assuming that it doesn't matter which group you're in. I'm assuming that fish consumption makes no difference and that it was all just random chance. In other words, I'm assuming that the null hypothesis is true. Then my third step is to deal them into groups. So before we dealt them into two groups, but here we have 5 groups of different sample sizes. So I'm going to deal them into 5 piles, and I want the size of the piles to match my sample sizes. So those are going to be 6, 6, 5, 5, and 5. So now I've got 5 piles of cards. Each of those piles have different values of omega-3 levels on them. So I could imagine, putting them into JUMP or an applet, making a graph, and I can summarize all of that information by calculating the R squared. Right? R squared is a way to look at the strength of the association, even though we have multiple groups to consider. And then we'll repeat this lots of times. So let's have the applet do this for us. We're going to show our shuffle options. I like to see the plot while I'm doing this. So it's going to take all of those points, shuffle them together, and deal them back out, and then calculate the R squared. So like here you can see the R squared is really low, 0.03. And that makes sense because all of these means are very similar to each other. So it doesn't seem like fish is really explaining much of the variation here, which makes sense. We're assuming that it's just random chance. So it kind of makes sense that we've got a pretty small R squared, but we want to know how large can R squared get just by random chance. So if we do it again, this time the means are a little bit more spread out from each other. So you've got like some groups that are higher and some that are a little lower. So the R squared was 0.14 here. This R squared came out to be 0.28. And I'm going to do a whole bunch of these. Let's see if my computer can do up to 10,000. Yeah, so now I've got a distribution of R squared statistics. Notice 0 is the very bottom because you can't have a negative R squared value. And the distribution looks a little different. We're kind of used to seeing symmetric null distributions. This one is skewed right, but nothing really changes about how we interpret it. So based on what we have so far, what do you think? Does this data provide strong evidence of an association between fish consumption and omega-3 levels? Pause the video for a second so you can think about it. So let's remember what we're looking at in this distribution. This is the null distribution. So this is showing us the values of R squared under the assumption that fish really makes no difference. Right? We're assuming fish makes no difference. In other words, we're assuming that the null hypothesis is actually true. These are the values of R squared that we would get if the null hypothesis were actually true. And then we're going to compare our real sample statistic from the real study to this null distribution. So we can find 0.506 maybe out here. So this is our real R squared value from our sample. And we can see it's pretty unlikely to get a value out there. So I'm going to say it would be unlikely. Haven't really quantified it yet, but I can see that it's out in the tail of the distribution. So it would be unlikely to get a value as extreme as ours, so as extreme as r squared equals 0.506, if the null were true, so if fish really made no difference. So to quantify that, let's count and see exactly how unlikely this is. So I'm going to go back to the applet and I'm going to put in 0.506 as the r squared value. Notice that we're counting the values that are greater than that. And that's because r squared, the larger the r squared gets, the stronger your association. And so I want to look at the values more extreme on the right side. And I can see out of those 10,000 shuffles, 32 of them were at 0.506 or more. So that's going to be our p-value. We counted all of them that were over here. You can sort of shade these values where you can see them. And our p-value that we got from the applet was 0.0032. So to state our conclusion, because our p-value is so small, we have very strong evidence, right? It's smaller than 0.01, which would be kind of our cutoff there. So we have very strong evidence to suggest, and we're always talking about evidence against the null and for the alternative. So to suggest that there is an association between these two variables. There is an association between fish consumption and omega-3 levels. And remember, when we say that there is an association, all that means is that at least one of these groups, A through E, at least one group is different from the others. So that's not exactly a satisfying conclusion yet, but we'll learn more later about how we can follow up and decide which groups specifically are different from each other. For now, we can just say that there is an association between fish consumption and your omega-3 levels.